Howdy. Let's look at the first section in Chapter 6 of the Practice of Statistics. This is a unit on random variables, covering both discrete and continuous random variables. So let's see what this is all about. The objectives for this unit, of course, to understand what is a random variable, but then to calculate probabilities using a probability distribution, calculate and interpret the mean and the standard deviation of the random variables, and to compute probabilities of certain continuous random variables as well. So first of all, we'll recall that a probability model describes the possible outcomes for a chance process and how often those things will occur. That's the probability model. So if we thought about flipping a coin 3 times, a fair coin, here's the possible outcomes. X is going to be defined as the number of heads that are obtained. So 0 heads means I got all tails, but 2 heads could be obtained any of these 3 ways. These 8 ways are the sample space of flipping the coin, but when I consider X to be the number of heads that I get, those are the only possibilities for the number of heads that I get. And you see these probabilities correspond to how many ways they could happen. Now, again, this is a fair coin that we're dealing with here. Here's a histogram representing the same thing. A random variable. Important to know this, it's the title of the chapter. A random variable is a numerical value that describes the outcomes of some chance process. The probability distribution of the random variable gives its possible values and their probabilities. A random variable is a numerical outcome or a numerical value representing the possible outcomes of some chance or random process. A random variable's got to be numerical. There's 2 main types of random variables, discrete and continuous. If it's possible to list all the outcomes, then we have a discrete random variable. So a discrete random variable takes some fixed set of possible values that we can list them out, and they may even go on and on and on and on, but we can list them out, and the probabilities have to be between 0 and 1. They have to add up to 1, and to find the probability of any particular event, these things are going to be disjoint, so we can add up the individual probabilities. I'll show you some examples of this, so don't let your head swim too much. But in a discrete random variable, we can list all the possible outcomes and assign probabilities. To find the mean, just like we've done before, we can talk about center shape spread. The mean of a discrete random variable is the average or the mean of all the possible outcomes, with each outcome weighted by its likelihood of occurrence. Again, I'm going to show you an example in just a second, but here's the way the formula would look. If I have all these different values and all their different corresponding probabilities, then to find the mean, I'm going to take each number times its probability plus the next number times its probability plus the next number times its probability, and so on and so forth, and add those things up. That's what this formula is telling me. That could be called the mu of x, the mean of x, or sometimes it's called the expected value of the random variable x. So that's what this symbol means. They are the same thing. The mean and the expected value mean the same thing. So don't be confused and think the expected value has to be something you actually expect. So if I was wanting to know the average number of, say, children in a household, and I came up with 1.7, that could be the answer, even though, of course, you don't get 0.7 of a child. The expected value means, over a long haul, how many of them we think we'll get. So here's this concrete example I promised. A baby's APGAR score is the sum of the ratings on each of 5 scales, which gives some whole number of a value from 0 to 10. Let X be the APGAR score of a randomly selected newborn. So the values are from 0 to 10. And here's the probability that those occur, which means if I looked at, say, 1,000 babies, I would expect 437 of them to end up with a 9, typically. Now, it really doesn't matter, and I think it's a valuable thing to do problems that you don't really understand the context of. But nevertheless, let's look just for a second at an APGAR score so you have a bit of understanding of what's going on here. Quick Google showed me that APGAR stands right here for appearance, pulse, grimace, activity, and respiration. Appearance is the color of the skin, pulse is the heart rate, grimace are the reflexes, activity is your muscle tone, and then respiration is the breathing rate. So you could read some of this or Google it yourself, but basically when a baby is born, they're quickly graded on a 0, 1, or 2 scale. For example, for respiration, it would say if they're not breathing, they get a 0. If they have irregular breathing, they get a 1. If it's normal, they get a 2. And so each of these numbers could be a 0, 1, or 2, and it's a quick way of identifying if the baby's in distress. It says here, babies who get a 7 or more are considered in good health. And a lower score doesn't necessarily mean that the baby's unhealthy. They just perhaps need some immediate medical care, such as suctioning the airways or whatever. So that's what's going on with this example. It says find the mean of the random variable x. Again, it's the same thing as the expected value. So 1 out of 1,000 babies gets a 0, 6 out of 1,000 get a 1, etc., etc. If I look at this in your brain, make a histogram. The values go from 0 to 10. That's what's on the horizontal axis. And then these numbers represent how high the bar sticks up. So what do you think a typical or average or mean or expected APGAR score is going to be? Somewhere over here in the 8 or 9 region, right? Most of the babies are over here. So this seems reasonable. It's good to think about this so I can assess the reasonableness of my answer in case maybe I've made a fundamental mistake. So we take 0 times 001, that's what this is, plus 1 times 006, 2 times 007, all the way down to 10 times 053. There it is. That's the mean. One way you could do this direct thing on your calculator is to put all the values in L1, all the probabilities in L2, multiply them in L3, and then add them up, and you'd get 8.128. Now, what does that mean? This is really important, interpreting the value in context. The mean APGAR score of a randomly selected newborn is 8.128. This is the average APGAR of many, 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 many randomly chosen babies. That's what the APGAR means. Since we use the mean as the measure of center, we can also use the standard deviation. So the formulas are similar to what we've done before. So here's the way to find the variance. Then the standard deviation will just be the square root of that. Now this looks awful, to be honest with you, but it's really not. So let's look at the formula. I see these x's. Those are the individual values. Now what is mu? Well, that's what we just found. That's the expected value. Squared, why do you suppose I need to square it? Well, if I don't, they'll all add up to 0. And then this probability is this number here. So here's the way it works. It's each of these numbers minus the mean squared times its likelihood of occurrence. Add all those up, and that's called the variance. The standard deviation is the square root of that. So let's revisit the APGARs and see. If you'll recall, the mean was 8.128. 8.128. So I'm going to take each of these numbers minus 8.128 squared times its likelihood of occurrence. 0 minus 8.128 squared times 001, plus 1 minus 8.128 squared times 006, plus 2 minus 8.128 squared times 007, etc., etc. That's the variance. Take the square root of that, That's the standard deviation. So a randomly selected baby's APGAR score will typically differ from the mean, which was 8.128, by 1.437. And of course, it's okay to round when you put stuff in sentences. This is the standard deviation or the variance of a discrete random variable, a variable whose values we can list out. Now let's talk a little bit about a continuous distribution. A continuous distribution takes all the values in some certain interval. The probability distribution of x is described by a density curve because I can't list all the values. If I could list them all, it would be discrete. Since I can't list them all, I've got some sort of curve, and the probability that an event occurs is the area under the density curve and above the values of x that are in that event. Again, I'll go through examples in just a second. Probability model of a discrete random variable assigns a probability between 0 and 1 to each possible value of x. But in a continuous random variable, like maybe y, we have an infinitely many number of values. All continuous probability models assign a probability 0 to each individual one, but intervals will have a positive probability. Again, this is something that sounds a little more confusing when it's written than it does with a practical example. So here's an example. The height of a young woman is approximately normal with mean 64 and standard deviation 2.7. It's a different population of young women perhaps than we've talked about in class. So if we choose one young woman at random, we'll call her height y. We get another young woman and another young woman and another young woman, and pretty soon we end up with this normal curve with a center at 64 inches and a standard deviation of 2.7 inches. Now I want to know what's the probability I choose a woman somewhere between 68 and 70 inches. That blue shaded region is the probability that I get a woman between 68 and 70 inches tall. It would be written like this. Again, for this problem, we're using a Y. Capital letters, English letters towards the end of the alphabet are usually the ones for random variables like X or Y or Z. Here's my graph. Now we go back and do something similar to how we did it in chapter 2. Take each number minus the mean divided by the standard deviation. Those are my Z scores. Look on my chart or possibly use the calculator to find that area. It's reasonable that this area is about 6%. Not so much 98%, that's everything below 70, or 93% is everything below 68. So in the middle here, it's about 6%. Means there's a 5.6% chance that if I randomly select a woman from this population, her height will be between 60 and 70 inches tall. In this unit, we talked about discrete and continuous random variables. We talked about finding the mean and standard deviation and variance of those discrete variables and how to use a density curve for continuous random variables.